So what if we place detectors in front of both holes and just close our eyes and not look? We don't know for sure what is happening when we are not looking, but we do know what the mathematics describing the waves tells us. When waves pass through a detector, the waves are altered so that they can no longer interact with one another. This means that the striped pattern will disappear even if we are not watching it. The detectors will cause this to happen on their own. However, the mathematics also says that each wave still simultaneously passes through both holes, even with the detectors present. But when we open our eyes and look, we always see the detector indicating that the marble passed through only one hole or the other, and never both. Each wave still simultaneously passes through both holes, even with the detectors present. But when we open our eyes and look, we always see the detector indicating that the marble passed through only one hole or the other, and never both. Not only are we not able to simultaneously measure the position and momentum of an object, the object does not even have a specific position or momentum until we observe it. No matter how long we wait after the marbles have hit the objects, each object will continue to have a probability of still being in the standing position. And each object will also continue to have a probability of being in the knockdown position. According to the mathematics describing the probability waves, neither outcome is certain. It's only when we open our eyes and look that we see only one outcome or the other. It's not just that we ourselves do not know the outcome until we look. It seems that even the universe itself does not know which object is standing up and which object is knocked down until we actually open our eyes and observe the results. To explain why this is the case and what this means about the fundamental nature of our universe, let us talk about spin. The apparent implication is that the universe cannot know ahead of time what the measurement of the spin will be, and the universe makes up its mind only when the spin is actually observed. The apparent implication is also that when the spin of one particle is measured, it sends an instantaneous message to its partner to spin in the opposite direction. If each particle makes up its mind about what direction it's spinning only when it's observed, then we need this instantaneous message from one particle to the other in order to guarantee that the two particles will always decide to spin in opposite directions when the detectors are aligned. This is true no matter how far apart the two particles have traveled away from each other. Even if we wait until the two particles are on opposite sides of the universe before we make our observation, this instantaneous message still seems to occur. Until we observe the particles, their spins are nothing more than probabilities. But we need to observe only one of the two particles for both of them to simultaneously decide in what direction to spin. If everything in the universe is made out of these particles, including the detectors themselves, then the detectors are also nothing more than a probability until they are observed. According to the mathematics describing the probabilities of the particles, passing through the detector is not what causes the particle's spin to decide to spin in one direction or the other. Passing through the detector entangles the detector to the particle, in the same way that the two particles are entangled to each other. The moment we look at the detector, it seems to send an instantaneous message to the particle so that the detector's measurement will agree with the spin of the particle. This is the same way in which the two particles seem to send instantaneous messages to each other.